Welcome back. This time we're going to introduce a kind of noise model. In fact, a whole class of noise models. We'll end up actually introducing quite a few different classes of noise models, but this is the right place to start. We're going to spend several lessons on noise models because there's a lot to learn about them. But for the moment, let's begin by reviewing. Early on, we introduced a kind of noise called AR1 noise. It's pure noise. It's a totally stochastic process. It depends on a parameter called phi, and to get the value, you take that parameter phi times the previous value, and then you add some random white noise. So a particular value is phi times the previous value plus some white noise. You may also recall that we were able to apply this procedure recursively. We say that this value is phi times the previous value plus white noise, which is phi times the value before that plus white noise plus the new white noise. And we can carry on that recursive process as far as we want. If we do, we end up with this kind of very long formula that we can express a given data value as an infinite sum of parameters to various powers times the white noise values, the present one and the past ones. That enabled us to compute the autocorrelation of this kind of noise value. We have for any lag greater than or equal to 0 that the expected value of a data value times a lagged data value is this double sum involving products of white noise values. Now, because these white noise values are white noise, we know that their expected value of products is the fundamental variance times the Kronecker delta. The Kronecker delta is 0 when the indexes are not the same, so the only terms that survive in the double sum are those for which the indexes are equal. That is to say, this offset is that offset plus the lag value. We end up being left with this expression, which we can algebraically manipulate to get this, which is the autocorrelation function for an AR1 noise process. By the way, I'll emphasize that this is the theoretical autocorrelation function. It's what we would get if we observed an infinite number of data samples. But of course, we can never observe an infinite number of data samples. The sample autocorrelation that we compute from an observed set of data will include some randomness, so it won't include this exactly. But as the sample size gets bigger, we'll get closer and closer to this exact expression for the true autocorrelation function of AR1 noise. Well, that's the autocovariance function, actually. And I can call it gamma, which I've often done. We can compute the autocorrelation function by taking the ratio of the autocovariance function values to the autocovariance at lag 0, which is just the variance. And that gives us the fact that for AR1 noise, the autocorrelation function is the fundamental parameter phi to the power of the lag. For lags less than 0, we can use the commutative property of multiplication to say that the autocovariance is phi to the power of absolute value of lag times this constant, and the autocorrelation is just phi to the power of absolute value of the lag. Well, we got the results so easily because we were able to do recursive application of the basic definition. And that enabled us to take our form and put it into an infinite series that all involved sums of factors times white noise values. I'll call those factors psi sub n, even though we know they're all equal to phi to the power of n. But I'm defining the quantities psi sub n as the coefficients of the white noise values of the lagged white noise values when expressing the data, the noise, as an infinite sum of coefficients times lagged white noise values. I'd like to introduce something that's very important and is often made good use of. It's called the lag operator. It's also called the backspace operator. I call the lag operator L because lag starts with L. A lot of people call it the backspace operator and call it B. What it does is it transforms a time series to its values one time step earlier. So if I take a time series and operate it on with the lag operator, what I get out of it is the same time series, only each value is what it used to be at one previous time step. That means that our original definition of an AR1 process can be written like this. The value now is equal to phi times the previous value plus white noise, which is phi times the lag operator on this value plus white noise. I can rearrange that, just bringing the lag operator over on the other side to say that this operator, the identity operator minus phi times the lag operator, when operating on the data values, gives a white noise time series. And we can think of this bold-faced one as the identity operator. It's the one which leaves the time series unchanged. Now I'm going to write it like this. I'm going to put capital phi operating on the time series, which is defined as this operating on the time series is equal to a white noise process. This defines the autoregressive operator capital phi. And this just says that when it is applied to a time series, it produces a white noise series. Now we might wonder, this autoregressive operator capital phi, does it have an inverse? Well, we could take an analogy from simple algebra and try this. If we thought of phi times the lag operator as a number, it might be equal to this expression, this infinite series on the right-hand side, which would give us this infinite series. And by the way, note that L, the lag operator to the power n, is also known as the lag n operator, because if I operate with the lag operator to delay things by one time step, and then operate with the lag operator again, I'll have delayed things by two time steps. Well, this is a fine thing to try. It kind of makes sense algebraically, but does it really work? That's a good question. Let's try this. Let's define a partial inverse. The partial inverse is the same expression, only instead of summing all the way to infinity, we're just going to sum to capital N. We're going to make a finite sum out of it. Then if I work out the algebra, I can see that our autoregression operator times this partial inverse has this form. That's the autoregressive operator. That's the partial inverse term. And if I work it out, almost all of the terms cancel except the very first, the identity operator, and the very last, which is our parameter phi to the power n plus 1 times the lag operator to the power n plus 1. Well, this is very useful because as n goes to infinity, that last term goes to 0 when the parameter has an absolute value less than 1. So, if the absolute value of the parameter is less than 1, then the inverse exists and is given by the expression that we thought it probably would be given by. Then I can do this. If I know that the autoregression operator times operating on x gives white noise, then x must be equal to the inverse of the autoregressive operator operating on white noise, which is this form. And notice I'm lagging the white noise values because that's the effect of the lag operator. And that gives me this expression. And when the absolute value of phi is less than 1, then so that this whole thing makes sense because the autoregressive operator is invertible, we say that the AR1 noise process is causal. Well, what if, instead of starting with the definition of an AR1 process and then deriving the fact that the autocovariances have this form, what if we started with the idea that the autocovariances have that form and wondered what kind of time series might have that property? Well, suppose we have a time series x with an autocorrelation function that follows this form. Let's define a new time series. This will be the x value minus our parameter phi times the previous x value. Well, now I can work out what is the correlation between, the covariance between two different values from this new time series. It's the expected value of this product, this term times this term. If I expand them all, I will get these four terms. And then I use the fact that the expected value of these two terms is just the given by the formula that we already assumed was the case for the X series. And I end up with this expression. Now we can consider separately the cases where J is greater than K, where J is less than K, and where J is equal to K. You can try this yourself if you want to take a detailed look at how it affects the absolute values. What we arrive at is the same in all of those cases, which is the expected value of the product of two of our Y values is gamma 0, the fundamental variance, times this parameter times the Kronecker delta. Well, that's very interesting because what we have is some constant times the Kronecker delta. Well, when the autocovariance of a time series is a constant times the Kronecker delta, that's the definition of white noise. What we've just shown is that if a time series is stationary and it has the given autocorrelation structure, the one we posited at the outset, then it is an AR1 time series because it is equal to each data value is that constant parameter phi times the previous value plus a white noise data series.